We invited Professor Doucet from Oxford University. Professor Doucet is working on Bayesian method and computational statistics, Monte Carlo simulation, and so on. Today, he will talk about computation method related to diffusion Schrödinger Bridge. So let's get started.
Thank you for the invitation. So I'm going to present a paper, joint work with Valentin de Bortoli, Jeremy Eng, and James Thornton. Valentin and James were basically student postdocs in Oxford, and Jeremy is an assistant professor in Singapore. It's a paper that was presented at NeurIPS last December. And it is not a paper about Monte Carlo simulation of Bayesian statistics this time. It's a paper basically about generative modeling. And in particular, we will explore this novel class of techniques, which is known as denoising diffusion models or score-based generative models. And we will show how we can improve this novel class of generative model, speed them up more exactly using techniques from known as Schrödinger Bridge. Okay. I'm just going to present first what we're basically trying to achieve. So I'm sure you're all familiar with the concept of generative modeling, and that, you know, even if you don't follow the machine learning literature, you've seen this kind of fake images which are generated by computers. So typically, what do you do? So you have that kind of database of natural images, database of celebrities, say, and then you're basically trying to develop some kind of novel stochastic model, which is able to essentially generate novel images that looks like the image in the database, but are not copies. Okay, so this kind of ideas is ubiquitous in machine learning, and it is used also obviously for music, waveforms, proteins. And basically, the thing we're doing with it is obviously we're not interested only in generating this kind of, say, fake images, but we want to use that later as some form of implicit model, say, in some inverse problem, or we want to use it in some kind of downstream task to create some kind of artificial training data for another, say, machine learning algorithm. Okay, so that's really very kind of important part of machine learning, and that has seen tremendous advance. There's been tremendous advance in generative modeling since basically the late 2010. Okay, so the first perhaps paper that will become very famous, there was this, obviously the VAEs, which can be thought as some kind of generative model, and then obviously the so-called GAN, generative adversarial network, which were basically were prominent over the past 5 years, and there's been also a class of autoregressive models. So a lot of literature, a lot of activities. I'm not going to talk about those models. I'm going to talk about a novel class of algorithm that has emerged really over the past 2-3 years. Okay? So the original idea was proposed in 2015, but people didn't pick it up because somehow they missed the connection. It was not really, you know, at the time, people kind of didn't understand exactly what to do, or to kind of use formalism, but it became extremely popular since 2020, 2021, where a group of Berkeley and a group of Stanford came up with some kind of like a very impressive empirical result. Okay, so this is what the class of model I'll be discussing today. Why am I particularly interested in those models? Well, there are two things. So first of all, this is the really new state-of-the-art kind of class of generative model in machine learning. There was a paper of OpenAI in May last year, which is entitled Diffusion Models Beat GANs on Image Synthesis. And indeed, there's been a flurry of papers on the recently over the past year, where it is shown repeatedly that according to various metrics, this class of this novel class of generative model outperform existing techniques. Okay. So that's actually quite interesting. There are drawbacks. So compared to GANs, generation of new sample is expensive. Okay, so that's one thing we wanted to work on. The second thing is also we wanted to understand better why theoretically it can even work. Actually. So I'll basically give you obviously more detail a bit later. So to start with, what I will do, I will describe this class of denoising diffusion models or Score-Based Generative Model. I will go through it, give some kind of introduction to this kind of concept, and then we will move to the main contribution of our work. Okay, so what is this basically the main idea between this kind of denoising diffusion model? It's very simple. Okay? So it's to say, really, so assume you have access, and I say you want to generate fake images, and you have access to a database of images that have been given to you. So how are you going to do that? How are you going to come up with a generative model to generate new images? But what you're going to think of doing is to essentially try to mimic some kind of denoising mechanism. So what you're doing is you pick your sample that have been given to you, your clean images, okay? One sample equals 1 images, and you noise it progressively, right? So that's the idea you're going to have. So you're going to noise progressively those samples so as to essentially destroy the information, okay? So that if you do that noise gradually long enough, essentially you had a clean image to start with on that set time, and you have really some noise, okay? So Gaussian noise. So formally, what does it mean? Well, you can think of this noising formalism as defining some kind of discrete time Markov chain. So X naught, your original sample, your original state of your Markov chain is coming from the distribution of natural images, natural images, say, and then you build this kind of sequence of state x1, x2, xn, which is essentially some kind of increasingly noisy version of the original images. So if you look at the joint distribution of x0, x1, x2, xn, where obviously it's just the distribution of a Markov chain. So this is P naught x naught, distribution of the natural images times this product of transition. Okay. So now the key idea is to say, okay, so we've been going from image to noise for just basically defining this Markov chain. So what we'd like to do now is to do the reverse thing, which is going from noise to images. Okay. So what I'm telling you is one way to think about it is to say, what about could we simply essentially reverse this noising mechanism that is sampling from X naught according to the distribution of the data on adding noise increasingly. So, well, yeah, you can. And what you do simply is you use this kind of forward-backward decomposition of the joint distribution of your Markov process. So whenever I give you a Markov process, okay, forward Markov process, you have also a backward representation of this Markov process. Okay, so really what you do, you can rewrite that the joint distribution of x2, x1, xn is the marginal distribution of xn at time n times the product of some reverse transition that take you from time xk plus 1 to xk, where those reverse transitions are obtained by the base rule. And here I will use the notation that the pk of xk is the marginal distribution of the sample at time k, which is obviously given by the Chapman-Kolmogorov equation. Okay, so assume you have now essentially this kind of like backward decomposition of the Markov chain. Right? Then you could say now, well, what I want to do, if I want to obtain some sample from P naught, X naught, the distribution of the image, well, at time n, I could sample from Pn, okay? And I know that Pn is going to be roughly Gaussian because the forward process has been such that I've defined it so that the marginal distribution at time is roughly Gaussian. So you're going to sample Xn from Pn, it's going to be quite easy to do that. And then you're going to basically do this so-called ancestral sampling or backward sampling or sampling state xk given xk plus 1 for time k equal n minus 1, n minus 2 till 1, okay, till 0 actually. So sorry, there's a little typo. You do that times 0. So in a sense, if you want to think of it, why basically there's a very simple forward process, which is just consists of adding noise to data. So that's very simple. But our generative model is basically the reverse process. We start from noise and you kind of denoise progressively by simulating those backward Markov transition so as to obtain at time 0 some sample from peanut. So that's the idea. Okay, so how do you put that in practice? There are obviously quite a few problems with that. So first, we need to see essentially how we put that. So in my context, think of it that peanut, this kind of, I say, original distribution of the data of the Markov chain is the distribution of the data. Okay. And you build transition, you're going to basically build transition such that time n, the marginal distribution of Pn, okay, the state of your Markov chain at time n, is approximately equal to some kind of so-called prior, I'm going to call that a prior distribution. It has nothing to do with Bayesian statistics. It's some kind of reference distribution. And in my case, it's going to be a standard multivariate normal. Okay, so I just want to define a forward process which is such that at time n, really, it's a kind of multivariate standard normal. Okay, so that will be my process, my noising process. It's very easy to do that. How do you basically go from any distribution, actually peanut, and you want to go to a standard multivariate normal, where you just use simply a kind of autoregressive Gaussian field. Okay, so you can have if you define a Markov chain, whose transition basically is such that at time basically xk plus 1 is equal to alpha xk plus square root 1 minus alpha square, some Gaussian noise. Obviously, you know that if alpha is strictly inferior to 1, then that's going to converge exponentially fast toward a multivariate standard normal. It's nothing but a discretized Arnstadt-Uhlenbeck process. Okay, so it's easy to define this kind of forward process. It's not like MC. We don't want to go very quickly from the original distribution to this kind of Gaussian distribution, multivariate normal distribution. We're going to want to do that gradually, not to destroy the information that was in the original image too quickly. Okay, so it's important to pick alpha. We're going to have to pick alpha quite close to 1. Okay? So you can do that, and then let's say the ancestral sampling, the original ancestral sampling procedure requires you sampling at time n for the marginal distribution Pn, and then using the backward transition. But because I know that Pn is approximately equal to this prior multivariate normal distribution, I can replace this initialization by sampling from this multivariate normal distribution. So that would be like the way I go from noise to essentially denoise that progressively to obtain a new images. So that's nice, but we still have a big problem to solve. So what's the big problem we have to solve? Where we know the forward transition of this Markov process, that is how to go from xk to xk plus 1 is just given by this simple autoregressive Gaussian. But how do you simulate from this kind of backward transition? It's not easy at all. Yeah? So we need to approximate those backward transitions. So if the forward transition corresponds to this autoregressive Gaussian process, well, you can approximate essentially quite easily the backward transition. So the backward transition, well, it's just a simple application of the Bayes rule that tells you that the backward transition from going from xk plus 1 to xk is basically equal to the forward transition probability to go from xk to xk plus 1 times the marginal distribution of xk at time k time divided by marginal distribution of xk plus 1. Okay? And then if you assume that alpha is very close to 1 and you do some Taylor expansion, you're going to find that, and we're going to make that things cleaner later on, but you can see that simply you can approximate this backward transition by something that looks like it's not an autoregressive process because this is a kind of explosive process here, but there's an additional term which is the logarithmic derivative of the marginal distribution of the forward Markov chain with respect to the state, which I will call score. Okay, so in the literature, it is called score. This is not like in statistics, it's not the derivative. This is not the Fisher score where you have the derivative with respect to some parameter. This here is the derivative with respect to the state. Okay. Okay, so we still we have this expression now, which is a little bit more tractable, but it tells you that if you want to approximate this backward transition, still you need to estimate this score. Okay, so how are you going to estimate that? Well, you're going to use something that looks like Fisher identity. Okay, but it's not quite Fisher identity because I don't have the standard like statistical parameter here. So it's the derivative with respect to some state. So we're just going to leverage the fact that the marginal distribution of xk plus 1, it satisfies this kind of Chapman-Kolmogorov equation, where here the transition, this thing is the transition, the probability to go from x naught to xk plus 1, which is tractable. And it is tractable. Why? Because I just have a combination of simple, essentially linear Gaussian transition. So if I combine all of them, this thing is nothing but a Gaussian distribution of argument xk plus 1 on the mean, which is a linear function of x naught plus some kind of variance term, which is independent of x naught. Okay, so importantly, I know essentially this term in closed form. And now I use this simple identity you can derive easily that tell you that the score I'm interested in is the conditional expectation of the gradient of the log transition. So this thing is the expectation of x naught given xk plus 1. Okay, so here now I've replaced that the score I'm interested in. You can think of it as a conditional expectation of a quantity which is tractable. Unfortunately, this conditional expectation, this is with respect, I said, the distribution of x naught given xk plus 1, and it's not tractable. Okay, so it seems I haven't achieved much. But when you do machine learning, on stat as well, obviously, whenever you see some kind of conditional expectation, well, you can replace it by some kind of regression problem. So what you can do is to say, well, okay, I'm not going to be able to perhaps estimate this thing perfectly, but I know that the true score, because it's a conditional expectation, I could rephrase it as if I were to take any function, measurable function, like the function of xk plus 1, if I were to minimize this essentially square error with respect to the joint distribution of x naught on xk plus 1, then the solution to this minimization problem is the logarithmic score I'm interested in. Okay, so I had this conditional expectation, it's not tractable. I reformulate that the conditional expectation can always be rewritten as the kind of regression function which minimizes the square error, okay, with respect to a joint unconditional distribution. On how do I use that practically? I say, well, obviously, I cannot parameterize all the kind of measurable function, but I'm going to replace S by some kind of neural network and essentially minimize instead this kind of locked function. Okay, so I'm not going to approximate the score, use a neural net to approximate the score at time 1, at time 2, at time 3, and so on and so forth. I'm going to use one single neural net to approximate all the score from time 1 to time n and learn the parameter of this neural net by minimizing this kind of sum of residuals. Okay, so that's the idea, and this is what people have been doing in the literature. Okay, so to summarize, I mean, this kind of algorithm is actually quite simple. So what people are doing, but how does this work? So you have your empirical data, okay, it's kind of a say database of natural images. And what you do, you noise those data progressively, and you use that to learn learn the neural network approximation of the score of the noisy data. Okay, so that's very simple. And once you've learned those scores, you say, well, I want to mimic ancestral sampling. So the way I mimic ancestral sampling is by at time n, I sample from a multivariate Gaussian, and then I mimic the ancestral sampling recursion, backward recursion, by sampling xk as a function of xk plus 1, because I don't have access to the true backward transition of this Markov process, but I can approximate it by the quantity where the score appears. Well, I replace the score by its neural net of approximation, and I obtain the sample at time 0 that looks like the sample in my database. Okay, so here this is an illustration in a very simple one-dimensional scenario. So here would be the distribution P0, distribution of the data. Okay, you noise your sample forward gradually. So at time n, you get something which has become roughly Gaussian. Okay, and then you want to simulate now the backward sampling, ancestral sampling procedure. So you restart from noise, you mimic this kind of ancestral sampling procedure that has required you approximating the score of this forward process, and you end up with samples that are basically approximate the original data distribution. Okay, so obviously in 2 dimensions it's not too impressive, but imagine that when we're doing that for natural images, you're living in the 10,000, 100,000 dimension. Okay. So this is what provides state-of-the-art for this kind of algorithm. So one way to think about it, which is quite maybe interesting, which is more elegant as well, is to try to think of what we are doing, not as this kind of discrete time process, but as some kind of like diffusion process, hence the noise, the name denoising diffusion that has been adopted by in the literature. So when you think really of what is done in the forward path, well, what you're having is that you have this kind of autoregressive thing, but if you do that really slowly in continuous time, that's simply becoming an Ornstein-Uhlenbeck process. Okay, so the Ornstein-Uhlenbeck, you start from the distribution of the data, you run this diffusion process till some given time t. Okay, and what is the equivalent, if you want, of ancestral sampling in continuous time? Well, it would correspond to look at a representation of the backward diffusion, okay, that is corresponding to this forward process. So if you have a diffusion that runs forward, it admits you can look at this process backward, and it's also a diffusion, okay? And this diffusion, okay, so here I've used the notation YT is X capital T minus T, which is the reversal process, the time reversal process. Then this diffusion also satisfied an SDE. And here we see indeed that the score that were appearing in my dirty Taylor expansion, they're coming from here. And indeed, you can make that rigorous instead of just doing it with this kind of Taylor extension. Okay, so essentially, there's a kind of nice interpretation of what we've done in continuous time. It's just like you have a diffusion forward, the backward process is also a diffusion, and you approximate this backward process by making 2 approximations. You replace the initialization of the backward process. You're going to initialize that by sample of Gaussian noise, because you know that PT is approximately Gaussian if you run your diffusion forward long enough, and then you're going to approximate the score by your neural network. Okay, so that's one way to think about it. That's good, but what can we say? What can we say theoretically about this kind of algorithm? So for those of you who are familiar, who've done a lot of MCMC, it might seem that this seems a bit crazy, because literally, when you essentially generate new sample, you generate sample through some kind of a process that looks some kind of non-homogeneous Langevin diffusion, and you're in extremely high dimension. You're like can be 1 million. Some of the example I showed you at the beginning from OpenAI are in 1 dimension. So you got it starting from some noise, and in finite time, you manage to obtain images in extremely high dimension. And how can it mix? I mean, like this is a Markov process. How is it possible that this thing is able to mix essentially? Your Markov chain is able to explore this really high dimensional space. Okay. So what we've shown is the following result. Okay. So we say, so this is a result which is somehow idealized. Okay, some assumption will not be able to, you'll not be able to check the assumption. The result has followed at least the first step towards having a theoretical understanding of this technique. We say, assume you're able to kind of have a neural net that approximates uniformly well the score at all time. Okay. Then you can bound the error between the distribution at time x0 that is provided by your generative model on the true distribution of the data. You can bound it by the sum of 2 terms. Okay. So one term is one term that essentially decreases exponentially fast with t, and this corresponds to the mixing essentially of the ideal time reverse diffusion. And I'm going to come back with that to that later. And then this term is a term which corresponds to the fact that you make error when approximating the term, the score each time step. So with this here, the dependence was in exponential. Recently, we got that down to linear, actually, but I haven't updated the slides. Okay. So maybe what is a bit miraculous is that, okay, so we have an error term that's coming from the score approximation. It's not quite surprising. But perhaps more surprising is that the error, which is vanishing exponentially fast with t, which is the error corresponding to the kind essentially mixing of the exact time reverse diffusion. It turns out that what we show can be shown easily is that the mixing of the backward process is entirely inherent. So the properties of this backward process, mixing properties, are entirely inherited by the mixing property of the forward process. But the mixing properties of the forward process is just the Ornstein-Uhlenbeck process. So essentially, you have extremely nice convergence result for that. It's the kind of simplest process you can think of analyzing in continuous time. So essentially, we are able to take the result, the kind of very neat result we have for the Ornstein-Uhlenbeck, convergence of the Ornstein-Uhlenbeck toward the Gaussian, multivariate Gaussian, and use that to essentially control the mixing of this time reverse process. So that's one of the nice bits that explain why there's no mixing issues when you run those algorithms, even in extremely high dimension. Okay, so that's nice, but it's still a problem. Okay. So it's still a problem. One of the problems is that for the time being, you do need to have a forward process that adds granularly noise long enough so that the marginal distribution at the final time step looks like a Gaussian. Okay, because then in your approximate ancestral resampling procedure, you replace this marginal distribution by a Gaussian, and then you simulate the backward dynamics. Okay. So it turns out that if you do that, so it means you're going to have to add noise for a long time and progressively, and so it takes quite a few steps in discrete time. But it means that at generation time, because you have to go all the way back from n to 0, generation is going to be very expensive. Okay. So, and you could say you could try to cut corner. You could try to say here think of it this thing as a 2-dimensional images, and then you would have noise progressively to it, and you add not enough noise so that essentially at time n your distribution is not, your sample are not noise. They are like still like some kind of easily identifiable corrupted version of the original images. Then even if you were able to essentially have an exact, you simulate exactly from the backward process, if you were to initialize that from a Gaussian, it wouldn't work. Okay, so that in a sense, that's a problem of this model. You really need to kind of take enough time to diffuse, to go from essentially clean image to noisy image, because otherwise you're gonna have, like, if you try to cut corner on stop before having diffusing long enough, then it's not gonna work. Okay, so we want to speed that up. So the way we're gonna speed that up is we're gonna speed that up by using this idea of Schrödinger Bridge. Okay, so we're gonna look at the following problem. So first, the Schrödinger Bridge is a problem that was introduced by Edwin Schrödinger in a 1932 paper, I think. It has had a kind of big impact in applied maths, optimal control, and probability. It's kind of very active area. And here we're not going to look at the kind of really theory behind it. We're just going to look at some kind of numerical algorithm so as to approximate the solution to Schrödinger Bridge. Okay, so how is that related to what we are trying to achieve? So the Schrödinger Bridge can be thought of in discrete time as follows. I define you some kind of reference density, and think of it, this is the joint density of my forward noising process. Okay, so remember that's this distribution here I'm going to consider is given by P naught X naught times the product of this forward transition, which are essentially autoregressive Gaussian process mode. Okay, transition. So this is your reference density, and I'm telling you I want to find the following thing. I want to find the joint density, okay, on the Markovian space. Okay, so like x0, x1, x2, xn. So I want to find this pi star. So this is the distribution that minimizes the Kullback-Leibler divergence between pi and the reference density p, subject to two constraints. Its marginal at time 0 has to coincide with the distribution of the data, and its marginal at time n has to coincide with this prior distribution that is my multivariate standard normal. Okay, so I want to find a distribution which looks like P essentially, because but it has fixed terminal condition. Okay, so if I can identify the distribution, a distribution that satisfies essentially that minimize the scale, okay, or then I will have a generative model. What do I mean I have a generative model? It's because simply, if pi star is available, then I can use ancestral sampling from pi star to obtain in finite time at 0 a sample from the distribution of the data. So at time n, I would sample from the marginal distribution of pi star, but because it satisfies the constraint, I know this would be a normal distribution. And then I would simulate the backward transition of pi star to obtain at time 0 exactly a sample from the distribution of the data, because by construction, pi star, the marginal distribution at 0 of pi star is the distribution of the data. Okay, so that's what I want to solve. Okay, so one thing that I'm not going to have time to discuss in too much detail is that it's closely related, solving the Schrödinger Bridge problem is closely related to essentially solving an entropy regularized optimal transport problem. Okay, so assume I'm going to use the following notation. If I give you any density on path space, okay, I write this following notation. This is the kind of joint distribution of x of the initial and terminal state times the conditional distribution of the remaining state x1 xn minus 1 gives one x naught xn. Okay, then I use this notation. If I use the chain rule decomposition of the Kullback-Leibler divergence, then I can rewrite the Kullback-Leibler divergence as the scale between this distribution, which only basically are on the initial and terminal times, plus the expectation of the scale between essentially the conditional distribution of the remaining state. Okay. So in particular, if I want to minimize the scale, it clearly what I need to do is that the conditional distribution of x1, x2, xn minus 1 given x naught xn has to be the same under pi as it is under p. This is the way I will cancel this term. Okay. Essentially, this Schrödinger bridge problem I reformulated, you can reformulate it as a kind of simpler problem, which is trying to find the distribution essentially on the initial and terminal states that minimize this Kullback-Leibler discrepancy. Okay, so I had this kind of dynamic version of Schrödinger bridge. I tell you, well, really what is tricky is not trying to kind of find out what's happening between x naught on xn. That is very easy. I know that the dynamic, essentially the conditional distribution of my Schrödinger bridge should be the same as the one under the reference dynamic. But what I need is really what is complicated is finding what is essentially the distribution on the initial and terminal states. Okay, you would do that by solving the scale minimization problem under constraint. Okay, and in particular, if you massage a bit the expression I've given you, you obtain the following thing. So assume I had given you a reference dynamic, which is such that the transition, the conditional distribution of xn given x naught under the reference dynamic is some kind of Gaussian. Okay, so this is Gaussian of mean x naught on variance sigma square. Then what you can see is that simply this kind of static Schrödinger bridge problem I've formulated is equivalent to solving this optimization problem, which is nothing but an entropy regularized optimal transport. And which is shown, it's been shown in full detail rigorously that as sigma goes to 0, this solution to this entropy regularized optimal transport converges in the true optimal transport in various metrics. So you have a specialist in Japan, is Mikami, who has a full book on this type of result. Okay, so that's nice. So now we say, well, okay, the way I could get around this problem of not diffusing long enough with the regular diffusion model, it would be to use this kind of Schrödinger bridge type to solve a Schrödinger bridge problem, because if I could solve a Schrödinger bridge problem, I would be guaranteed infinite time to have essentially a generative model that goes from Gaussian to distribution of the data. So that's all nice for the time being, but I haven't explained you how we can solve this problem. Okay. Okay, so what we're going to do, we're going to use an algorithm which has many names in the literature to solve the Schrödinger bridge problem. So this algorithm is known as iterative proportional fitting. It is known also as the Simcorn algorithm when you're dealing with measures which are essentially discrete measures, and that has been popularized by Marco Cuturi, a former postdoc at the Institute of Statistical Mathematics, and it's kind of very used in the machine learning community nowadays. And it's actually also was somehow mentioned heuristically in the original paper by Schrödinger. So he had come up, even if it's a 1930 paper, with some kind of way, not only formulated the problem, but he had come up with a way to kind of solve it. It's quite remarkable. Obviously, you have proof of convergence, but it's still pretty impressive. Okay, so how does it work, this algorithm? So the iterative proportional fitting is some kind of essentially alternate projection algorithm. So remember what we have. The original Schrödinger Bridge problem, you want to minimize the KL between pi and p, and you have two constraints. You want that the marginal at time 0, pi naught is p data. You want the marginal at time n, pi n to be equal to p prior, the multivariate normal. And here you just basically have an iterative algorithm where you're just going to enforce one constraint at each time step. Okay, so you start, you're going to set pi naught, you're going to start it as the initial reference measure, and then you're going to say, well, I want to minimize at odd iteration, you're going to minimize the KL between pi and pi to n, and you're just going to enforce that you want the terminal constraint, okay, so that pi n is the distribution p prior, the multivariate normal. On that even iteration, you minimize the KL, and you just basically enforce the constraint that pi naught is equal, the marginal distribution at time 0 is the distribution of the data. Okay. And what you can show is that as n goes to infinity under very mild regularity condition, this iterated algorithm converges to the solution of the Schrödinger bridge. And now we want to understand how we can use that algorithmically. So what does it mean? Okay, that's nice, but is there a way to implement these kind of things algorithmically? So here we're going to do something which is simple. So we're just going to look first at the first iteration of the IPF. So first iteration of the IPF. So I want to solve the minimization problem. I want the KL. I want to minimize the KL between pi and pi naught. And pi naught is p. This is the initial thing. So I use the chain rule for the KL divergence. And basically, I know what I'm interested in doing. Well, there's this term. I'm not going to be able to do anything about that. Okay, that's the way it is. And I want to minimize this term now. So if I want to minimize this KL, I'm going to have to minimize this term. And this term tells me that essentially the conditional distribution of the state essentially from time 0 to time n-1 on the pi should be the given the terminal condition should be the same as on the p. And I have the constraint that pi n is p prior, so that gives me a representation of the solution. So essentially what we say, first iteration of IPF, well, this is this kind of, think of it as this backward process. So this is a process that you initialize time n by p prior, Gaussian, and then you do this kind of backward transition, and these things are the backward transition associated to the forward noising process. But this thing, you think of it, is nothing but what we are doing in standard denoising diffusion model. Okay, so the first iteration of iterative proportional fitting is exactly what people are currently doing in denoising diffusion model. But here, well, this is what I told you. If you do that, on basically if the original marginal distribution Pn was too far from p prior, if you just run one iteration of this algorithm, you won't have converged. And what do I mean by you won't have converged? It means that basically the marginal distribution at time 0 of this backward process is not going to be anywhere close to the distribution of the data. It would be if really n was very large enough on that you have given time basically to the algorithm for Pn to be close to Gaussian, but otherwise it's not. Okay, so what you do? Well, you iterate IPF. So to iterate IPF, what you have to do, well, you have to solve this other constraint minimization problem, where this time the constraint is on the initial essentially distribution of the process. And you use exactly similar argument. And what do you get? You get that the pi2 is a joint distribution, which can be thought as the distribution of some kind of forward process, which at time 0, you have the distribution of the data. And then you have a forward process on the transition of this forward process are obtained by reversing the transition of the backward process pi1. Okay, so you keep doing this kind of time reverse process. So again, you had, so at first iteration, you have IPF1 is the time reversal of the forward process pi naught is initialized by p prior time n, that defines a backward process. The second iteration, the time reversal of the backward process, pi1 is initialized at p data to different pi2. On you iterate again, the time reversal of the forward process pi2 is initialized at p prior time n, and so on and so forth. Okay, so you do all this inverting of time reversal dynamic. On each time you feed it a different initial condition. Okay, so that's what you're doing. And to approximate this recursion, and I'm not going to go through that because we're not going to have time. To approximate this recursion, you can use each time you're going to have to essentially reverse those dynamics, okay? And you're going to use the same trick that we are using for the standard denoising diffusion model, that is this kind of score identity and score matching on neural network regression. Okay, so I'm just keeping the detail, but the point is that we have a way to essentially implement numerically this kind of algorithm, and it only requires us having samples from p data and p prior. We never ever need to have access to analytical expression for this distribution, which is key in the generative model context, because obviously we don't have access to p data, we just have access to some kind of sample from p data. Okay, so this is the algorithm. It looks, so the way it works is that literally you have at each iteration, you're going to train some kind of neural net to learn the score of your process, which you essentially time reverse in the following step. And here again, on you iterate. Okay. So here I'll give you an illustration of the algorithm. So think of it as your two-dimensional distribution here. So you go forward. Okay, first step, this is your noising process pi naught, and you obtain something which doesn't correspond to, it's not noisy actually, okay? It's not noisy enough, so in particular, it doesn't look like anything like normal. So what you do, doesn't matter, you do IPF, so you start from a normal, a Gaussian sample, and then you use a backward dynamic that has been obtained by essentially score matching, by estimating the score of the forward dynamic. And this is your first iteration of IPF. Okay, so that doesn't work as we expected. So now you reiterate. So you restart the next iteration of IPF, you restart from the distribution of the data, and then you simulate a forward dynamic, which is obtained by time reversing this backward process, this backward dynamic, which so you need to estimate in particular the score of this backward process. You run like that and you iterate. And you see here that literally after 5 iterations, we get some kind of proper generative model. Okay. So if you want to formulate that a bit cleanly in terms of continuous time, it is possible to do it. So, it was quite clean in the context of the standard context, I would say, a denoising diffusion model to reformulate everything with the Ornstein-Uhlenbeck of the time reverse diffusion. You can do obviously exactly the same for iterative proportional fitting. So in this case, the Schrödinger bridge is essentially a KL minimization on path space, okay, on path measure of diffusion. Okay, you can write down iterative proportional fitting, and you can see that the solution of the iterative proportional fitting for this Schrödinger bridge problem is essentially a collection of forward and backward diffusion whose drift evolve according to this recursion. So here, this is the score of backward process, and here, this is the score of forward process. Okay, so in a sense, you can see that really what we are doing is just essentially simulating approximately diffusion that depends essentially at each iteration on the score of the previous process. Okay, so I give you another example here. So this would be, say, the data distribution, and you basically try to use this kind of, you diffuse not long enough, so you don't have noise sample. So if you do that, obviously, then when you do score-based generative model, when you come back to time zero, you don't have anything that looks like the original data distribution, but by using this kind of diffusion Schrödinger bridge algorithm, you are able to do that. So we have example, for example, for generating images. So nothing compared to OpenAI, but we have a very limited computational budget. So it's we cannot compare in terms of computational power, but we're still able to generate image in about 3,000 dimensions using this type of algorithm that looks pretty realistic, actually. Another thing you can do is that obviously this thing is not limited to a simply generative model, but it can essentially can be used to solve any kind of generic Schrödinger bridge problem. So for example, I can give you two data distribution. So here's a spiral on this S, and I can tell you, I want to find essentially the kind of optimal interpolation, in the sense that this is the distribution that minimize that solve the Schrödinger bridge problem. Okay, so here this is what we've done. So basically, we have these two empirical data distribution that are given to us, and we solve a Schrödinger bridge problem between them, and essentially that gives us a collection of distribution that interpolates smoothly between the original data distribution to the terminal one. Okay. Okay. So just a quick recap of what we've done. So I've presented denoising diffusion model. I know some of you might not have been familiar with this class of model. So it's a very kind of simple idea, high-level idea. So you just add noise to your data, and you essentially try to denoise, learn a denoising procedure. So it's very powerful. So we kind of shed light on the kind of theoretical properties of this denoising diffusion model. So in particular, I think one thing which is interesting is that although you simulate process that looks like some kind of non-homogeneous large dimension in high dimension, there's no mixing issues. And we've shown that there's one way to speed things up, which is to reformulate everything as a Schrödinger bridge problem. We came up with this kind of way to approximate the Schrödinger bridge solution which can be interpreted really as a generalization of the existing algorithm for generative modeling, because the first iteration of our algorithm coincides with what people do in the literature. And we found that you always improve results in terms of like, compared to the existing techniques. There are some challenges. The complexity remains very high. So this is really something that is actually quite computationally intensive. It's because when you do things, say, for images, you still simulate essentially process in extremely high dimension. You do essentially diffusion in pixel space. So this is, if you have an image which is 1 million pixels, you have to run a process which is in 1 million dimensional. So that's quite expensive. Okay. So there's been a lot of other techniques that have appeared recently to speed things up. So people are improving that. One thing which is clear, so we have this link to optimal transport, okay? But this is really, if you wanted to use this kind of algorithm to do, say, optimal transport with L1 metric, we don't know how to do. We have no idea to do. And finally, there's still a lot of things to do in terms of analysis, because we have some convergence result, but for example, we make a very strong assumption by assuming that our neural network is able to approximate the score uniformly well, and we have absolutely no clue how to verify such an assumption, and I'm actually pretty sure it's not satisfied. So a lot of things would have to be improved. If you're interested in this kind of problem, I recommend those those 3 papers. So this is the first paper that was proposed in the literature, but people didn't pick it up at the time. And these are the 2 papers, like the NeurIP 2020 and iClear 2021, that essentially popularize this class of techniques and provide really state-of-the-art. And our paper appeared, as I said, NeurIPs last December and is available on my webpage. Thank you.
Thanks for the presentation and showing us excellent results. Now, let's move to the question or comment sessions. So if you have any comments or questions, please turn on your microphone and speak.
It's very impressive because I was interested in time reversal, as you knew. Maybe the score is what we call the osmotic pressure or something, right? It's actually it's some of the osmotic pressure and the force that reverse the drift. And but your starting point of the story is quite surprising, and I never thought that we can we can construct generative modeling by such way. Is it so?
Yeah, I mean that's not my idea, and I have to admit it's quite amazing work actually.
But I can understand why you are so much interested in this topic. It's quite impressive. Or song or some this guy, and it's comparative to the methods based on DNN, or maybe better.
So I mean, everything they use when they learn this kind of scores, they use neural net, and they use very specific neural net. But you know that then they get results. In terms of generative modeling, it's like state of the art. It beats GAN, it beats everything. That's why there's actually an explosion of papers over the past 6 months now, because it seems that in many domains, not only in this domain, those image domains, this provide like remarkable results. But I mean, it's still quite mysterious why it works so well. Yeah, so we're trying to understand, but there's still issues. From a pure forgetting about the generative modeling side, the fact that we can approximate time reversal has obviously numerous applications in Monte Carlo, as you know very well. And we've been playing with that to use these kind of ideas outside the generative modeling context. Once to simulate standard diffusion bridge. So that is really when you have a diffusion that is pinned down at 2 points at time 0 at time t. And more recently, I've been looking at another way, which is essentially to kind of use this type of ideas to get some kind of optimize, like Jarzynski-Crookes identity somehow. So you know that basically Jarzynski and Crookes identity as based on this kind of extended target distribution, which is based on the quasi-reversal of the proposal. What we propose is to use instead the kind of approximation of the true reversal of the process, so as to obtain like estimate of the free energy with lower variance. And we have preliminary result that indicates it can bring significant gains actually. So there are applications outside this generative modeling actually, which are I think quite relevant.
And your main contribution is also we can optimize the forward dynamics. This is one of the main contribution of your work.
Yeah, the contribution of this paper, the main contribution has been the theoretical contribution, where we understand the kind of, we could analyze the error of the standard methods And the second contribution is this numerical solution of Schrödinger Bridge that has never been presented in the literature. So we have a way to solve Schrödinger Bridge numerically in really high dimension, whereas all existing techniques I was aware of, they were limited to like 2-3 dimension. Or we can do it like successfully in like 100,000 of dimensions. So that's really the main contribution, is the kind of Schrödinger Bridge. Your kind of numerical solution to Schrödinger Bridge, actually.
As you pointed out, this is in a sense similar to some smoothing problem, but there's big difference because there's no data between target and goal. Starting point and goal.
Yeah, exactly. There's no smoothing, but you could use that. This kind of idea can be used for doing some. They can be used to do your rare event things you are doing with time reversal. You could use this kind of idea to do that as well. You can use it. So one thing I didn't mention, so we have a forthcoming paper. So everything I presented here is for unconditional simulation. Okay, but one of the main interests for this kind of techniques is not because people want to generate, fake images or fake voice. That's not the main application. The main application is where one of the main applications is to use this kind of generative model as some kind of implicit prior for kind of inverse problem or Bayesian inference problem. So in this case, you can. So what we've shown is that you can use this type of algorithm to also simulate approximately from a posterior distribution, when the only thing you know to do is to simulate from the joint distribution of the parameter of observation, on nothing else. It's not even ABC context because you don't even have access to a prior distribution. You just have like a simulator that can simulate forward. That's it. That's all. So there are all these things that people are doing currently, and so there are applications which are actually directly for some kind of Bayesian statistics problems.
Thank you very much.
Thank you.
Another questions? So I have general questions. So you showed the S structures data. So that's the number of DSP process required for the accurate backward sampling depends on the structure of data.
I'm sorry, I'm not sure I understood your question. I apologize. Can you repeat? Sorry.
Okay. The number of the diffusion, Schrödinger Bridge process required for the accurate backward sampling depends on the structure of data.
Yeah, it does actually. So what I didn't talk about here is that there's no miracle. So you think of it in continuous time. I give you two distribution, P0, P1. Then you say in continuous time, the kind of solution to the Schrödinger Bridge is going to be a diffusion process. Okay? Essentially, when you discretize it, well, obviously, if the drift of the Schrödinger Bridge solution of the Schrödinger Bridge is very steep, you would need a lot of time steps to approximate it properly. So some are, yes, it's not explicit in what I've written, but it is indeed underlying that essentially the number of step n you can use it cannot be ridiculously small, because if it were, then you would have an extremely poor approximation of the drift of the underlying diffusion. And then it means the algorithm won't work well. So yes, you answer the question to that. Yes, practically, it's very difficult to diagnose, obviously, because you don't know the true Schrödinger bridge. So we have diagnostic we are using when we are doing we implementing things numerically. But yeah, you're right entirely.
Okay, thank you. So, do you have any other questions? Okay, so I have another question. So you imposed constraints onto time 0 and time n.
Yeah.
So can we impose some other constraint to the middle of the process? I don't know what kind of situation it corresponds to, but if some kind of measurement has implemented in the middle of the dynamical process, we want to need some constraint into the middle of the, we want to impose some other constraint in the middle of the process. So does it possible?
So yes, it is. So in the generative modeling context, it wouldn't really make sense, but generally speaking, you can do this. And this is called this multi-marginal Schrödinger bridge, which instead of enforcing 2 constraints, you can have multiple constraints. So there's some papers on that. We haven't looked at adapting our algorithm to this scenario, but I'm pretty sure it's feasible because what I've seen of people doing that is like they have some kind of equivalent of the so-called sin corn for the multi-marginal problem. So if they have that, given what we are doing can be thought as some kind of continuous state space version of that, I conjecture we could adapt that to this problem. Typically, what I've seen, people are using this kind of formulation when they have this kind of distributional regression problem. So essentially, the distribution, you're trying to do a regression, but basically, your unknown is a probability measure, and you have measurement at various time steps. Yeah. But yeah, that does exist. Yeah.
Thank you. Any other questions? Okay, so.
Oh, okay. How about periodic solutions? It's very different problem.
I know it's a very different problem. No, I'm not even sure I follow you entirely. So what do you mean by that?
Oh, it's a kind of double-ended solution. We fix the starting point and also ending point. If the starting point and the end point coincides, it's some kind of periodic orbit. That's maybe it related to find some periodic orbit to us.
You could, I mean, you could do that because, I mean, there's no reason in what we are doing. If
some dynamical system people are interested in the unstable periodic orbit.
Okay.
I'm not sure this is good idea or not, but some people really interested in finding unstable periodic orbit in, for example, Navier-Stokes equation.
Mm-hmm. So I don't know if it can be reformulated as Schrödinger bridge problem, but clearly, if you can formulate the Schrödinger bridge where the 2 marginal at time 0 and n are the same. There's if the dynamic doesn't preserve this measure, then you're gonna, your Schrödinger bridge is gonna do something, I would say sensible. Otherwise, the solution is obvious. But yeah, no, you could do this. So I don't know. I don't know if there's an interpretation as a kind of Schrödinger bridge in their context. But yeah, there's no reason that you couldn't solve it with the two same marginal actually.
Thank you.
Any other questions? So if there are no other questions, let's finish this seminar. Thanks for Professor Doucet again.
Thank you. Goodbye.
Yeah, thank you.